night, the tropics, the Pacific Ocean, sandy bottom, almost nothing is visible. And then something strange emerges from the darkness. A creature drags two halves of a coconut shell and moves on two arms with such a ridiculous, wobbly gait that scientists gave it a special name, stilt walking. This is the coconut octopus, and it does something that was considered impossible for an animal without a backbone until 2009. It carries a tool that it doesn't need right now. The shell doesn't protect it as it walks. Its head and body are completely exposed, and any predator could grab it. But the octopus knows that the shell will be useful later, in a new place, when it needs to hide. It plans. It carries something for future benefit. Until this moment, such behavior had only been observed in monkeys and some birds. And here we have a soft-bodied creature with no bones at all. Now, let's pause and talk about this body, because it's structured as if it were designed on another planet. Before we continue, please let us know where you're watching from and subscribe to the channel. Thank you. The octopus has no skeleton, none at all. No external skeleton like a crab, nor an internal one like ours. The only hard part in its entire body is a small beak made of chitin, right in the center, where all 8 arms converge. Everything else is soft, flexible, and capable of changing shape. This allows the octopus to squeeze through any opening as long as its eye can fit through. Not its head, not its body, but specifically its eyeball, because that's the largest non-compressible part. In 2016, an octopus named Inky lived in the National Aquarium of New Zealand. One night, it lifted the lid of its tank, crawled out, slithered across the wet floor, and found a drain pipe. The pipe was about 50 meters long and led straight to the ocean. Inky squeezed into it and disappeared. It was never found. No one knows where it is now, or if it's even alive, because octopuses have short lifespans. But the very fact of escaping from a closed aquarium through a 50-meter pipe demonstrates a level of ingenuity that we don't typically expect from a creature without a backbone. Now, let's talk about blood. The octopus has 3 hearts. 2 of them work solely for the gills, pumping blood through them to get oxygenated. The 3rd heart pumps this enriched blood throughout the body. But there's one problem. When the octopus swims, the 3rd heart stops. It simply ceases to beat. So after each swim, the octopus gets exhausted, and most of the time it prefers to crawl along the bottom rather than swim. By the way, its blood is blue. In our blood, hemoglobin, a protein based on iron, makes it red. But in the octopus, instead of hemoglobin, there's hemocyanin, a copper-based protein. It's less effective at transporting oxygen in warm water, but excels in cold depths where oxygen is scarce. However, this system has a weak point. If the acidity of the water changes, if the acid level in the ocean rises, the octopus simply can't deliver enough oxygen to its organs and dies. And the acidity of the world's oceans is currently rising. This isn't a future prediction, it's a process that's already underway. But the most astonishing thing about the octopus isn't its heart, its blood, or its escapes from aquariums. The most remarkable aspect is its brain. More precisely, how this brain is distributed throughout its body. The total number of nerve cells in an octopus is about 500 million. That's roughly the same as in a dog. But here's the difference. In dogs, almost all neurons are concentrated in the head. In octopuses, 350 million neurons, more than 2/3 of the total, are not in the brain but in the arms. Each arm contains its own nerve center, which functions almost like a separate brain. In October 2024, scientists from Robin Kroger's group created a 3-dimensional map of the nervous system of one arm of a dwarf octopus and discovered a variety of chemical signals, dopamine, serotonin, acetylcholine, that had previously only been found in the central brain. The octopus's arm is not just a tentacle that grabs and pulls, It's an independent nervous system with its own chemistry, its own reactions, and possibly its own perception of the world. And here's where things get personal for me, as it made me rethink everything I knew about evolution. In 2015, scientists fully sequenced the octopus genome for the first time, and the results were such that they had to be read twice. The genome size is 2.7 billion base pairs. The number of genes that code for proteins is over 33,000. That's more than in humans. Scientists expected to find evidence of large-scale genome duplication, as was the case with our ancestors, the vertebrates, but there was none. Instead, there was something else. The octopus experienced a significant increase in one specific family of proteins, protocaterans. These molecules are responsible for the complexity of the brain in us, for how neurons find each other and connect into networks. In vertebrates, protocaterans are one of the key tools for building a complex nervous system, and the octopus arrived at the same solution, independently, on its own. Considering that our common ancestor lived over 500 million years ago and had nothing of the sort. But that's not all. The octopus genome turned out to be filled with so-called jumping genes, transposons, pieces of DNA that copy and insert themselves into different places in the genome. In humans, transposons occupy about 45% of all DNA. And here's what was discovered in 2022. The same types of jumping genes that are active in our hippocampus, the area of the brain responsible for memory and learning, are also active in the octopus, and also in those parts of the brain associated with memory and learning. Two evolutionary paths that diverged 500 million years ago and have not intersected since have arrived at the same molecular mechanism for building a complex brain. Nature, it seems, solved the same problem twice, in two different ways, but using the same tools. And this makes you wonder, perhaps complex intelligence is not a coincidence or a unique stroke of luck for vertebrates, but a regularity that evolution arrives at again and again, given enough time, and the octopus is living proof that it has done so. Right now, while you're listening to this, somewhere on the ocean floor, a creature with blue blood, 3 hearts, and a brain scattered across 8 arms is solving a problem that no one has set for it, just because it can. The octopus sits on a coral reef, and you can't see it, not because it's far away or small, but because it looks like a piece of that reef. Its skin changes color in a fraction of a second, becomes bumpy, rough, and mottled, and now it's indistinguishable from the rock it sits on. This isn't a trick or an exaggeration. The octopus changes its appearance faster than you can blink, and it does so with a precision that any artist would envy. How does this work? Its skin has 3 layers of special cells, and each layer does its job. The top layer is chromatophores. These are tiny pigment sacs, with muscles arranged around each one like spokes around a wheel. When the muscles contract, the sac stretches, and the color becomes visible. When they relax, the sac compresses to a point, and the color disappears. Thousands of these sacs work simultaneously and independently of each other, creating incredibly complex patterns. Beneath the chromatophores lies the second layer, iridophores. These cells contain no pigment. They reflect light and create metallic sheen, iridescence, and rainbow hues. Even deeper are leucophores, which scatter light and act as a white background over which the 2 upper layers paint their picture. 3 systems, 3 levels, all working simultaneously, in real time, without delay. And here's where the real mystery begins. The octopus is colorblind. It has only one type of light-sensitive cell, a single photoreceptor. For comparison, humans have 3 types, and it's thanks to their combination that we distinguish colors. The octopus lacks this ability. It sees the world in shades of gray, like a black and white movie, yet its camouflage perfectly matches the colors of its surroundings. It copies shades it cannot see. How? There are several theories. The first relates to the shape of the pupil. The octopus's pupil is not round like ours. It's W-shaped, wavy. This shape can cause chromatic aberration, when light of different wavelengths focuses at slightly different points, and from this displacement, one can deduce color without color receptors. But there's a second theory, and it's much stranger. Scientists have found the light-sensitive protein rhodopsin directly in the skin cells of the octopus, not in its eyes, but in its skin. Its skin can sense light itself, without the involvement of the eyes, without commands from the brain. In experiments, the skin cells of a related squid reacted directly to light and changed pigmentation on their own. The octopus's skin likely has the ability to see, not in the way we do, not as a picture with details, but it distinguishes light and shadow, and possibly wavelength. It's skin that is simultaneously both a screen and a sensor. And since we're talking about screens, here's what was discovered about sleep. In 2023, scientists from the Okinawa Institute of Science and Technology published a paper in Nature that turned our understanding of how animals sleep upside down. They observed sleeping octopuses and found that their sleep consists of two alternating phases. The first is quiet sleep. The body is still, the skin is pale, and breathing is steady. The second phase occurs about once an hour and lasts for about a minute. During this active phase, the octopus's arms begin to twitch, its eyes move, and bright flashes of color run across its skin, changing patterns, waves of pigment. Researchers implanted special probes in the brains of the octopuses and recorded neuronal activity. It turned out that during active sleep, the octopus's brain operates almost the same way as when it's awake. This closely resembles the rapid eye movement phase of sleep in mammals, the one during which we dream. And during quiet sleep, rhythmic waves of brain activity were recorded in octopuses, similar to so-called sleep spindles, oscillations that in humans are associated with memory consolidation during sleep. Two types of animals that diverged on the evolutionary tree 550 million years ago, having nothing in common except for an ancient ancestor resembling a worm, have arrived at the same architecture of sleep, independently of each other. What flickers on the skin of a sleeping octopus, whether it dreams of reefs or predators, we don't know yet, but the brain is clearly processing something at that moment. Now, let's discuss what happens when an octopus loses an arm. A predator grabs it, the octopus breaks free, and the arm tears off. For some species, this isn't even an accident, but a strategy. The octopus discards a tentacle to distract the attacker, much like a lizard sheds its tail. But there's one important difference. A lizard's tail regrows in a simplified form, without normal vertebrae and muscles. An octopus's arm regenerates completely. A layer of new cells forms at the wound site, beneath which a so-called blastema accumulates, a cluster of cells that haven't yet determined what they will become. And in about 100 days, from this mass, a fully functional new arm grows, with muscles, suckers, a nerve cord, and all the receptors. It works just like the original. The octopus literally regrows a part of its own nervous system, and the severed arm, while it's still alive, continues to move, responds to touch, and may even try to pull food toward itself, because it has enough neurons to act autonomously. It doesn't yet realize it's no longer attached to the body. Lastly, I want to talk about pain. For a long time, it was believed that invertebrates do not truly feel pain, that they have reflexes, pulling away from heat, moving away from damage, but no subjective experience. In 2013, nociceptors were discovered in cephalopods. These are specialized nerve endings that respond specifically to tissue damage. These receptors don't just activate once and calm down. They go through sensitization. After an injury, the area around the damaged site becomes more sensitive, and this lasts for a long time. This is pain memory, where the body remembers where it was hurt and enhances protection of that area. When an octopus had its arm injured in an experiment, the neighboring suckers began actively probing the painful spot. as if the local nervous system was trying to figure out what happened. This heightened sensitivity was alleviated by painkillers, and octopuses in experiments remembered which chamber they were given anesthetic in and deliberately returned there. They sought relief. They didn't reflexively pull away. They consciously went to where the pain subsided. In November 2021, a group of scientists from the London School of Economics analyzed over 300 scientific papers and presented a report to the British government. Their conclusion was direct and unequivocal. There is compelling evidence that cephalopods are capable of subjective experiences. In April 2022, the British Parliament passed an animal welfare law that officially recognized octopuses, squids, cuttlefish, and crustaceans as beings capable of feeling pain for the first time in history. Not reflexively, but truly. Now the government must consider their welfare when drafting any new laws. A country with one of the oldest parliamentary traditions in the world looked at the scientific data and said, yes, this creature feels, and we must take that into account. An octopus lives from 1 to 3 years. That's its entire life. During this time, it must learn to hunt, master its territory, memorize the map of the reef, build a shelter, develop habits and strategies, and die. It has no parents to show it how to live. It has no group to pass on experience. Its mother stops eating after laying eggs. She sits over the clutch for weeks, sometimes months, hardly moving, fending off predators and fanning the eggs with fresh water. She exhausts herself to the limit and usually dies before the hatchlings emerge. She will never see them. The male dies shortly after mating. No knowledge is passed on to the next generation. No skills, no tricks, no found paths to food. Every octopus that comes into the world starts from absolute zero. With no teachers, no examples, no culture, and despite all this, each new individual manages to solve puzzles, start using tools, learn to open jars, and remember the faces of specific people in its tiny life. An octopus in an aquarium distinguishes one staff member from another, even if they're all dressed in the same uniform. That same Inky from New Zealand, who later escaped through the drain pipe, reacted differently to different aquarium workers. It reached out to some, turned away from others, and splashed water at a few. This isn't coincidence or reflex. It distinguished people and formed relationships with each. And here we come to something that has long been taken lightly. Octopuses have personalities, not in a metaphorical sense, but in the same way psychologists talk about personality in humans. Stable individual differences in behavior that persist over time and manifest in various situations. There are exploratory octopuses that crawl into every crevice and try everything new. There are cautious observers who watch for a long time before acting. These differences are reproduced in repeated tests and even predict how successfully a particular octopus will tackle a new task. Bold individuals solve puzzles faster but make more mistakes. Cautious ones take longer but make fewer errors. Each octopus has its own strategy, its own style, and this isn't programmed by genes. It's formed over its short life. Now, something quite unexpected. Octopuses are considered solitary animals. They don't live in groups, don't hunt in packs, and don't build collective shelters. But in 2022, Peter Godfrey Smith from the University of Sydney published a paper showing that octopus solitude isn't so absolute. In Jervis Bay, Australia, gloomy octopuses live at an unusually high density because there are few good shelters and plenty of food. And there, cameras recorded over 100 instances of octopuses picking up mud, shells, or seaweed from the bottom and throwing this debris using a jet stream from their siphons. To throw something accurately, the octopus had to reposition its siphon into an unusual position under the membrane between its arms. This isn't a random movement. It requires intentional body adjustment. Some of the throws hit other octopuses, And here's the important part. Individuals with dark coloring, which in octopuses is associated with aggression, threw harder and hit their neighbors more often. And those who were hit dodged or raised their arms toward the thrower. Octopuses were throwing debris at each other. Purposeful throwing of objects at peers had previously only been documented in chimpanzees, capuchins, and elephants. This behavior requires an understanding that another is nearby, that you can affect them, and that throwing is a way to do so. And it's worth mentioning what octopuses do in captivity, because it's in aquariums that their inventiveness becomes particularly noticeable. They open jars with screw-on lids from the inside and outside. They take equipment apart. One octopus in the Santa Monica Aquarium dismantled the water recirculation hose, and water flowed onto the floor for 10 hours until staff arrived in the morning and found 200 gallons of water on the floor. Other octopuses redirected the water stream from their siphons onto a lamp that bothered them, flooding it until it turned off. They play with objects with no apparent purpose, chase plastic bottles around the aquarium, disassemble and assemble Lego constructions, and drag toys around. Play without a practical goal has long been considered a sign of complex consciousness, and it has only been documented in mammals and some birds. And now we come to the final question, the most complex one. Does the octopus have consciousness? Philosopher Thomas Nagel wrote a famous paper in 1974 titled, "What is it like to be a bat?" The essence was that even if we study every neuron of a bat, we won't know what it's like to perceive the world through echolocation. Subjective experience cannot be reduced to descriptions of neural circuits. With the octopus, this question becomes even more complicated, because a bat at least has one center of experience, the brain in its head. An octopus potentially has 9, a central brain and 8 semi-autonomous nervous systems in its arms. Does the octopus have a unified sense of self? Or is it something like a federation of 9 agents, each processing its part of the world and sharing only part of the information with the others? When an octopus's arm explores a crevice while the brain looks in another direction, who makes the decision, the brain or the arm? And is there even one entity making decisions? In 2012, a group of neurobiologists signed the Cambridge Declaration on Consciousness. This document officially stated for the first time in the history of science that not only mammals and birds, but also cephalopod mollusks, possess the neurological basis for conscious experience. The octopus was included in this list not as an honorary exception, but as a being whose brain, behavior, and physiology leave little doubt. Its genome contains more genes than a human's. Its skin senses light. Its arms make decisions without the involvement of the head. Its brain goes through the same phases of sleep as ours. It throws debris at those it dislikes. It plays with things just for fun. It feels pain and deliberately seeks relief from it. It recognizes people by face and relates to each in its own way. And despite all this, it lives a maximum of 3 years, dies without passing on anything it learned, and its offspring start all over again. The octopus retreats into a crevice, blocks the entrance with stones, and falls asleep. Flashes, patterns, waves of color begin to run across its skin, which no one will ever see. Perhaps it dreams. Perhaps its arms dream their own dreams. We've built the idea of mind around a single model, our own. A backbone, a skull, one brain, 2 eyes, one consciousness. And then, on the ocean floor, a creature was found that proved all this could be done differently, and that another version also works. Thank you for subscribing to the channel and liking the video.